Welcome. Today we'll be discussing the converse of the Pythagorean theorem. So let's get started. Uh, let's start by taking a look at this introduction question. Well, remember that the Pythagorean theorem, which is stated as a squared plus b squared equals c squared, it only applies when we have a right triangle. So now the question is it possible to have a right triangle whose given sides are 3, 4, and 5? So how can we state if we can create a right triangle using those three sides? Well, let's start by drawing our right triangle. If this is going to be a right triangle, then therefore there must be a 90-degree angle in here. So we just create it here. And now what do we know? What is one thing that we know about this right triangle? Well, one thing that we know about this right triangle is that the longest side, it's always the hypotenuse. So if we want to make a right triangle whose sides are going to be 3, 4, and 5, then 5 must represent the hypotenuse. Because I know that if in any right triangle, the longest should be the hypotenuse. Therefore, then this three lengths, 5 is the highest value, so therefore 5 should represent the hypotenuse. So now if 5 represents the hypotenuse, then perhaps we can make a connection with the Pythagorean theorem. Because I know that the Pythagorean theorem states a squared plus b squared equals c squared. So now let's think about this for a second. We have stated before that the Pythagorean theorem only applies if we're talking about a right triangle. So if the question is it possible to have a right triangle with these three sides, then it's sufficient to show that these three lengths satisfy the Pythagorean theorem. Because if it satisfied the Pythagorean theorem, then therefore we must have been talking about a right triangle. So let's see. Is it possible for us to make the Pythagorean theorem to be true given these three sides? Well, I know since 5 is a hypotenuse, then 5 should be represented by c. And a squared and b squared doesn't really matter because we're adding them. So in this case, we can make it 3 squared and 4 squared. And if this is true, then we can conclude that these sides create a right triangle. Well, let's see if this is true. 3 to the second, that's 9. 4 to the second, that's 16. That's 25. And 25 is actually 25. So let's think about this for a second. We just shown that in any, we just shown that with these three line segments, we have properly satisfied the Pythagorean theorem. So therefore, we can create a right triangle whose legs are of a value of 3, 4, and 5. So this is actually the main idea that we'll be discussing today. How is it that we can use the Pythagorean theorem to draw conclusions? Because right now my conclusion is that yes, we can actually create a right triangle using these lengths. And notice that the way that we did that is by satisfying the Pythagorean theorem. So let's actually expand this idea. Because now let's take a look at this triangle that we do have here on the right hand side. We know one thing for sure. We know that if we make our value c to be exactly 90 degrees, then we definitely have a right triangle, because that's just how we define right triangles. But what if instead of making the right triangle, what if we instead of making that same angle c, what if we make it into a value that is less than 90 degrees? So what kind of a triangle will we be creating if we let that angle c to be exactly less than 90 degrees? Well, let's think about this for a second. We have a triangle, and we know that one of their angles, interior angles, it's exactly less than 90 degrees. So this definitely satisfies the condition of an acute triangle. Because that's actually how we have defined acute triangles. An acute triangle, remember the definition of an acute triangle? An acute triangle is any triangle where one of their interior angles is exactly less than 90 degrees. And that's exactly how we have defined that. So therefore, in any angle, I'm sorry, in any triangle, if one of the angles is less than 90, then we know it's an acute triangle. But what if, now we change this a little bit. What if we make that same angle to be greater than 90 degrees? What if we make that same angle, but now instead of making it less than 90, because I know if that is exactly 90, it's a right triangle. If it's less than 90, then when it's an acute triangle, then what kind of a triangle will we be having if it's greater than 90 degrees? Well, if we think back about our definitions of triangles, uh, any triangle that has an interior angle which is greater than 90 degrees, we will always categorize that as an obtuse triangle. And again, this is just definition. So let's just recap here. If we have a triangle whose 90 degrees, then we know it's a right triangle. If that same angle is less than 90 degrees, it's an acute triangle by definition. And if that same angle is greater than 90 degrees, then it's an obtuse triangle by definition. But now, how are these three ideas uh, put together? Like, what is the relationship between everything that we've been discussing so far? Well, notice that if we have a right triangle, then the Pythagorean theorem holds true. Then when can we actually draw a conclusion when we have an acute triangle and an obtuse triangle? Well, for that, we have what we define as the converse of the Pythagorean theorem. And the converse of the Pythagorean theorem is just a tool that we use to categorize triangles based on their sides. And we can encounter three different situations. We can encounter a situation where the actual Pythagorean theorem holds true. So if the Pythagorean theorem is true, if a squared plus b squared equals c squared, then our conclusion is that we have a right triangle. And that's something that we discuss on the introduction question. But we could also have a situation where perhaps a squared plus b squared is actually greater than c squared. And again, recall that at least in this case, c will always be the longest side. So I know that if it's exactly equal, then it's a right triangle. So what happens if a squared plus b squared is actually greater than c squared? Well, when we encounter this situation, then we have an acute triangle. Because now let's think about this for a second. If I know that it's exactly 90 degrees, then we have a right triangle. So now, if we make this angle to be less than 90 degrees, then we're actually reducing the size of C. So as angle C starts getting smaller, notice that right now, all I'm doing, I'm just creating, well, hopefully, I don't think I'm doing it by scale, but I want for you to see that as C is getting smaller, the side opposite of it, it's also getting smaller. So therefore, if I know that it's exactly 90 degrees, I have a right triangle. So if this side is actually smaller, or this side square is actually smaller than the two leg square, so that means that this side must be less than 90 degrees, and therefore it fits the definition of an acute triangle. So what would happen if we actually have the situation where a squared plus b squared is actually greater than c squared? Well, if it's equal to c squared, we have a right triangle. If it's less than, I'm sorry, if c squared is less than a squared plus b squared, that's an acute triangle. Nope, sorry, typo, because notice I'm doing here the same. So we want to see the case where it's actually greater than. Oops. We actually want to see the case where it's actually uh, greater than. Well, if c squared is greater than a squared plus b squared, then we must be dealing with an obtuse triangle. Because it's actually the opposite, because I know that if it's exactly 90 degrees, then therefore this c squared has a fixed length. So if we start making our length c, if we start making our length c to be greater now, and if we start making our c side greater, then notice that as I keep increasing my length of c, I'm also increasing the value of angle c. So as c is getting larger and larger, therefore my opposite angle must also be getting greater and greater. And if I know that if when it's equal to, it's exactly 90. So if I start making if I start making c larger, therefore my angle must be increasing in size. And it's just going to be a point that's going to be more than 90 degrees, and therefore it is an obtuse triangle. And this is very important because this is how we're going to categorize triangles now. If it fits, if it fits the Pythagorean theorem, then it must be a right triangle. If a squared plus b squared is greater than c squared, then we have an acute triangle. And if a squared plus b squared is less than c squared, then we have an obtuse triangle. So let's actually just think back about something very, very fundamental, which is when exactly is it that we have an actual triangle? And again, this is something that we have discussed previously, but no, it never hurts to just remember. Uh, the only way that we can create a right triangle is that if two of the sides, if you add them up, it's actually greater than the third. And these three conditions must be true in order for us to properly say that we have a triangle. Doesn't really matter if it's a right, obtuse, or acute. So just remember this. The sum of the lengths of any two sides of a triangle will always be greater than the leg of the third. So if I were to add a plus b, that always has to be greater than c. If I were to add a plus c, whatever value that is, it should always be greater than b. And which one am I missing? If I were to add b and c, whatever value that is, it will always be greater than a. So given three sides, if you add two of them, it should always be greater than the third. And if that's not true, then you just definitely don't have a right, or you just don't have any triangle whatsoever. So these are the rules. This is how we can properly categorize triangles. So let's actually just do two examples. Let's just do two examples now. So this task is asking if a triangle is formed with the sides having the lengths given, is there an acute right or obtuse? So right now, notice that we are already saying that, no, that's not what it's saying. So what we want to do now is see, well, what kind of a triangle do we have here? I guess just because of the time that we do have right now, let's just do it verbally. So notice that first we got to check, do we have a triangle? Well, let's just check this real quick. 6 plus 8 is definitely greater than 10, so we're good. 6 plus 10 is definitely greater than 8, so that's good. 10 plus 8 is definitely greater than 6, so that's good. So notice what we did real quick. I just added two sides, and I make sure that it was greater than the third. And you just got to check all three. So we know for a fact that we have a triangle in here. But now the question is, what kind of a triangle do we have? Well, we can use the Pythagorean theorem. Right now I can see that 10 is the largest, so I can make this to be my C. So let's see what kind of situation or what kind of scenario do we have here. Is this equal to? Well, let's find out. So in this case, 6 squared, that's 36. 8 squared, that's 64. Now, is that equal to 100? Yeah, definitely. 100 is equal to 100. So notice that these three values fit the Pythagorean theorem. So therefore, my conclusion is that we do have a right triangle. But now let's look at B. Let's just do B and C. Let's take a look at B. Real quick, do we have a triangle? Well, let's see. If I add 4 and 6, if I add 4 and 6, that's 10. That's definitely greater than 8. If I add 4 and 6, that's definitely greater than 8. If I add 6 and 8, okay. If I add 6 and 8, that's definitely greater than 4. So we're good. And if I add 4 and 8, that's definitely greater than 6. So notice that what I did real quick is I just checked to see if we have a triangle at first. And I saw that we do have that because it doesn't matter what combination. If I add 2 of the sides, it's always going to be greater than the third. So now that I know that I have a triangle, what we're going to do is say, well, what kind of a triangle do we have? Well, let's find out. Well, in this case, notice that 8 is the longest, so I'm going to make 8 to be my C. And let's just see what kind of Pythagorean theorem, let's just see if this makes the Pythagorean theorem to be true. So notice that that's why I'm putting a little question mark here, because we don't know if it's actually equals to. So let's just see if this is true. 4 to the second, that's 16. 6 to the second, that's 36. Now, is that equal to 64? We know that if I add this 2, that's 52. So notice that this is not true. Notice that 52 is not equal to 64. But I know that 52 is greater than 64. So what we have shown so far is that a squared plus b squared is less than c squared. And given the situations that we do have here, we just stated that if a squared plus b squared is less than c squared, we have an obtuse triangle. So therefore, 4, 6, and 8 can only create an obtuse triangle. So notice how we're using the Pythagorean theorem. Now, real quick on example C, let's see what kind of a triangle do we have. But before you check before you check what kind of triangle you have, you must check, do you have a triangle? Well, let's add 2 sides. So is it true that 1 and 4 is 1 plus 4 greater than 6? Well, nope, that's not true. Notice that if I added 2 sides, and the addition of those 2 sides is definitely not greater than the third. So therefore, I cannot even create a triangle at all. So in this case, no possible triangle. I can kind of see that there's a typo here because positive is with double S. So notice that we just shown that we cannot even create a triangle given the sides that we do have here, because we just show that if I add 2 of the sides, it's not greater than the third. So therefore, I cannot even create a triangle at all. So hopefully this was helpful, and I'll see you next lesson.